Today we are going to see the graph theory. The graph components are points or nodes or vertices, and those vertices or nodes are connected to each other by lines. These are called as edges, and these lines may be directed or undirected. Now, as shown in the figure, a graph is a pair of sets that is V, E. Here V is the set of vertices and E is the set of edges connecting the pairs of vertices. So, V is equal to A, B, C, D and E, 5 vertices set, and E is equal to AB, AC, BD, CD, DE, that is 5 edges set. The types of nodes: the root node and leaf node. The root node is the ancestor of all other nodes in a graph. It does not have any ancestor. Each graph consists of exactly one root node. Generally, you must start traversing a graph from the root node to leaf node. Leaf node. In a graph, leaf nodes represent the nodes that do not have any successors. These nodes only have the ancestor nodes. They can have any number of incoming edges, but they will not have any outgoing edges. The degree of vertex. It is the number of vertices adjacent to a vertex V. The notation for degree is DEG in bracket V. The degree of vertex is the number of edges incident on a vertex V, and the self loop in the graph is counted twice. So, the degree of vertex can be considered under the two cases of graphs from degree point of view, that is undirected graph and directed graph. Undirected graph has no directed edges, whereas in directed graph each vertex has an in degree and an out degree. Now the types of graph. First, undirected graph. Second, directed graph. Third, weighted graph. And fourth, cyclic graph. Now, one by one, we will see the definitions of those types of graphs. First is undirected graph. An undirected graph is a graph in which all the edges are bidirectional. That is, edges do not point in any specific direction. As shown in figure 1, there are 1, 2, 3, 4 vertices are there, and those vertices are connected with edges, that is 1 to 2, 2 to 3, 3 to 4 and 4 to 1. But if we observe that there is no any direction for the edge in the graph, so we can say that this is a undirected graph. Now, as shown in the side figure 2, this is a undirected graph. Here the degree of A is equal to 2, means as there are two edges meeting at vertex A. The degree of B is 3, as there are 3 edges meeting at vertex B. The degree of C is 1, that is, as there is one edge formed at the vertex C. So, C is called as the pendant vertex. The degree of D is equal to 2, as there are two edges meeting at vertex D. The degree of E is equal to 0 because there are 0 edges from the vertex E. So, E is called as an isolated vertex. Again, one more example, that is in figure 3, the degree of A is equal to 2, degree of B is equal to 2, degree of C is equal to 2, and degree of D is equal to 2, and the degree of E is 0, means the vertex E is an isolated vertex and the graph does not have any pendant vertex. Now we will see one theorem based on the degree of vertices. Show that the sum of degree of all vertices in a graph G is even. So first step is each edge contribute 2 degrees in a graph. Also, each edge contributes 1 degree to each of the vertices on which it is incident. Hence, if there are n edges in graph G, then we have 2n is equal to degree of V1 plus degree of V2 plus degree of V3 up to plus degree of Vn. Therefore, 2n is always comes as the even. So, as shown in the previous figure 3, here the degree of A plus degree of B plus degree of C plus degree of D and plus degree of E is summed, and it is coming as 2 plus 2 plus 2 plus 2 plus 0 means is equal to 8, and again 8 is an even number and is equal to 2n, where n is the number of edges. As shown in the previous figure, there are 4 edges, 1, 2, 3 and 4. So 4 into 2 is equal to 8, and 8 is the sum of degree of all vertices, and it is always coming as an even number. Now, second type of graph, that is directed graph. A directed graph is a graph in which all the edges are unidirectional, that is, the edges point in a single direction. As shown in the figure 4, the 1, 2, 3, 4 are the 4 vertices of the directed graph, and the edges are connected within those 4 vertices. So, the edge connecting from 1 to 2 is having a direction from 1 to 2. Suppose the edge is in between 2 to 4, but the flow is from 4 to 2. And again there is another edge that is flowing from 2 to 4. Now the vertices in 3 and 4, there is an edge coming from 3 to 4, and the vertices in 3 and 1, the edge is coming as 3 to 1. So based on the direction of the graph, it is again of two types. In degree of a graph. In degree of a vertex V is the number of edges which are coming into vertex V. So the notation is degree plus of V. Out degree of a graph. The out degree of a vertex V is the number of edges which are going out from the vertex V. The notation is degree of minus V. See here two examples which are giving the vertices set in degree and out degree. So as shown in the figure 5, there are total 1, 2, 3, 4, 5, 6, 7 means A to G set of vertices are there, and there is an edge between A to B, B to C, C to D, D to A, etc. So these edges are unidirectional, and based on the direction arrow, they are either in degree or out degree. Now you can tally the in degree edges as well as out degree edges for each vertices in the table shown as, that is A in degree 1, out degree 2, etc. In this way, you can tally all the vertices set with the in degree and out degree count. Now we will see one more example, that is as shown in the figure 6. There are 5 vertices are there, A, B, C, D and E. Each vertex having either in degree or out degree or both. So the table is showing the vertex with in degree and out degree count. You can tally again the vertex against in degree and out degree count. Now, the third type of graph is the weighted graph. In a weighted graph, each edge is assigned a weight or a cost. Consider a graph of 4 nodes as shown in the figure below. Here in the figure 7, the graph is called as the weighted graph because as you can see, each edge has a weight or cost assigned to it. If you want to go from vertex 1 to 3, you can take any of the path. For example, to go from 1 to 3, there are 3 paths are available. That is the path from 1 to 2, 2 to 3. Second path is directly from 1 to 3. One more path, that is 1 to 4 and 4 to 3. And each path or each edge assigned some weight value. Now, if you count, the total cost of each path will be as follows. The total cost of 1 to 2 to 3 is equal to 1 plus 2, that is 3 units. The total cost of 1 to 3 is only a 1 unit. And the total cost of 1, 4, 3 will be 3 plus 2, 5 units. So, based on this unit count, we will see that 1 to 3 is the low cost path and we can follow this 1 to 3 path to go from vertex 1 to 3. Now, one more type of graph, that is the cyclic graph. A graph is cyclic if the graph comprises a path that starts from a vertex and ends at the same vertex. The path is called as a cycle. An acyclic graph is a graph that has no cycle. So, example of acyclic graph is the tree. A tree is again undirected graph in which 2 vertices are connected by only one path. A tree is an acyclic graph and has n-1 edges, where n is the number of vertices. So, each node in a graph may have one or more multiple parents node. However, in a tree, each node comprises only one parent node. So, as shown in figure 8, a root node has no parent, that is the node number 1. A tree cannot contain any cycles or self loops. However, the same does not apply to graphs. Now, the definition of various types of vertices. First, pendant vertex. By using the degree of vertex, we have 2 special types of vertex. A vertex with degree 1 is called as the pendant vertex. Again, as shown in figure 9, the vertex A and B has degree 1. So, it is called as the pendant vertex. Isolated vertex, a vertex with degree 0 is called as an isolated vertex. So, as shown in figure 10, the degree of vertices A and B are 0. So, these are called as the isolated vertices. One more term, that is adjacency. Here, the norms of adjacency are: in a graph, 2 vertices are said to be adjacent if there is an edge between the 2 vertices. Here, the adjacency of vertices is maintained by a single edge that is connecting those 2 vertices. In a graph, 2 edges are said to be again adjacent if there is a common vertex between the 2 edges. Here, the adjacency of edges is maintained by a single vertex that is connecting the 2 edges. So, in this graph, we will see the adjacent vertices and adjacent edges. So, A and B are the adjacent vertices because there is a common edge between A and B, that is AB. A and D are again the adjacent vertices as there is a common edge AD between them. AB and DE are the